Today we're going to see our first little equation. Our first little real equation for the semester. What's one of the most basic things I can calculate if I have a bunch of numbers? Like, let's say I have a bunch of ages of people, right? Oh gosh. Poor little dude. So I just have a bunch of ages, 4, 9, 15, 25, 48, whatever. Okay. What's one of the most basic things I can calculate?
Mean.
The mean. So let's talk about what the mean equation is and then just make it more mathy, right? So if I ask you how do you calculate a mean, you are going to tell me a lot of words. So how can somebody tell me how you calculate the mean of any set of data? Yes.
You add up all the numbers in the data.
Yeah, add them all up. Oh, you're dying too. Oh man. Oh dude, add them all up. Divided by
Number of numbers.
the number of data points. We'll say. Yeah, I like it. Would everybody roughly agree with that definition? Okay. Math people in general don't like that many words. I have a specific reason, that being that I can't write too well, so it'd be better for me to write less. So the symbol what's a more official word for add? It's funny thing is it's got the same number of letters. Sum, right?
Is that supposed to be a 2?
Where? This thing?
Yeah.
Yeah. Actually, that almost doesn't matter. I just want to put some numbers up there. So the official kind of word for adding is sum. The Greek letter for S is sigma. So we use capital sigma. And what that symbol means is add up these. So the symbol sitting by itself doesn't make sense. It's sort of like if I ask you, you all know what the square root of 9 is, right? 3. What if I ask you, okay, do this? What would you say? Do this. What would you say? What's missing?
Numbers.
Yeah, square root of what, Jeff, right? So if you just have this symbol sitting by itself, it actually doesn't make much sense. It's exactly like just having this sitting by itself. I have to put next to it what you want me to add up. What are all these officially called? I kind of gave it away down there, but what are all these called?
Same points.
Data points. They're the data. They're the answers to the question, correct? Before I got the answers, how could I represent what all the answers could be? So like back in algebra, when I didn't know something, like how old somebody was, how could I represent that? X, I love it. So if I want to add up all the numbers, add up all the variable values. So far I've written add them all up. That's what that means. And then divided by, what letter do you think I want to use for the number of data points? N. I love you. Okay. So there's our first little official formula. And it's a formula, it's kind of a nice little step because I don't need the formula. You guys all know how to calculate the mean. Add them all up, divided by how many there are. So this is a nice little baby step into what the formulas are going to look like. The symbol that we use for the mean depends on if I'm talking about a population or a sample. So we're going to see this in a few different places. Let me see. Do you guys remember? Oh, this is a funny little thing. Do you guys, anybody ever watch much football ever? So a while back when the Super Bowl was coming, they would have like graphics in stone, in Roman numerals, what Super Bowl it was. Do you guys agree with me, if anybody? And even if you've never seen it, you kind of can see this in your mind's eye, yes? But Super Bowl 50 was hilarious because does anyone know the Roman numeral for 50? L. So it would have just been this big stone L that would drop. That would have been really kind of funny, but what's my point with this? When I have a population, I want to use a symbol that kind of communicates, oh yeah, this is the real shit. So we're going to use Greek letters. So this would mean a population mean. So a Greek letter mu. That's the U with the little extra leg. We saw that on the warm-ups. It's on the Greek sheet that I put up in Canvas. So the way you say that is mu. Okay. Yes?
Wait, what is x again in the main equation?
What does x mean in algebra?
Just a blank.
Like if I see x in an equation, like x plus 2, what could x be?
Anything.
X could be anything. So in this case, x represents all the possible values. So when I see sum up x, that means add up all the possible answers I got, right? Okay, I like it. So what about if I have a sample? If I have a sample, we actually call it x bar. And it's the same formula. Just this different symbol if it's a sample. Okay, that'll work. All right, nothing amazing yet. I want to kind of focus on this summation symbol though, real quick. Let me give us some different data just to make this quick. Oh. I want to focus on this guy, because this guy right here, this symbol right there is going to be in a lot of our equations. It kind of makes sense. I'm going to have to add up stuff a lot and then do other stuff to it to calculate stuff. That kind of makes sense. So if my data, let's say is 1, 4, 9, 11. So let me write it like this. Here's my data, 1, 4, 9, 11. What's the sum of x in that case?
25.
Yeah, so you just have to add those up. 25, kick ass. Is that cool? Why was this easy? Because it asked me to sum up something and I know all the values for it. So what about this? Now you gotta be really careful. What does that say to do? Doesn't say square the sum. If I wanted to square the sum, I would have to square the sum. That would be 25 squared, right? Which I think is 625. This says to add up what? I have to add up x squares. Do I have the x squares yet?
No.
So I can't add them up. So what do I want to do? I want to make a list of x squares. Let me stop for a minute. If in an equation you see sum of x squares, just like this, if you don't have them yet, go make them. And then you can add that shit up. So whatever's after the sum, you have to have them first. And then, of course, you can add them up. You guys, trust me, a lot of our equations are going to have this symbol in it. If you just cover it, you go, oh, I need a bunch of those. Let me go make a bunch of those. So what are a bunch of those? 1, 16, 81, 121. And then you add them up. You're all like, come on, math boy, add them up. No, what do you get? When you add them up, what do you get? All right, so you get 219, right? Okay. Thanks, Rail. All right. Does everybody kind of, let me do one more and see what you guys, same data, but what I need is I need to know the sum of x minus 2. Don't say anything, just think about it for a minute. So again, if you cover that, you know what you need. If we don't know that yet, go figure it out and then add them up. So now I can make like an x minus 2 column, so what goes here? If x is 1, what's x minus 2? Negative 1? 2? 7? 9. So what do you get when you add these up? So now I can sum up the x minus 2's because I have a bunch of x minus 2's. And what do you get? Man, you guys really do. You know, we're not going to play along with you, man. You already added that shit, didn't you? Yeah, I did. All right, so. Real quick little side note, just this doesn't mean a damn thing. I subtracted 2, right? 4 times, correct? Because there's 4 numbers. Do you see how the sum was 25? It should be 8 less, and it is. What I just said has nothing to do with it. It's just a quick little side note. So to be honest, I didn't add the shit up. I just subtracted 8. Okay. Does everybody get that idea? We're going to see formula. Again, this is going to be one little piece of the formula. If you cover that, oh, I need a bunch of those. Let me go make them so I can add them up, and then I put that number there. Okay. I like it. In fact, we're going to see that probably next time. So this is our first little formula. This is for the mean. Mean of a population, the mean of a sample. Okay. Now, there are situations, let me explain one real quick nice situation. If you wanted to describe to somebody the housing costs in San Diego, you could use words, and we could all have various words for that. But what's wrong with giving somebody the average house price, the mean house price? Can somebody imagine what's wrong with that? Or let me bring it down a step. What if, I'm going to take all this away, is that cool? What if I was about to start working at a company, and the company has 3 employees and 1 CEO, right? So I got somebody who makes $38,000 a year, $40,000 a year, $42,000 a year, and then the CEO makes $500,000 a year, right? And I ask somebody, hey, what can I expect to make when I start working there? And they tell me the average. What is the average, by the way? Can somebody calculate that for me real quick? Is 155. The average? I think it's 155,000. Double check me. I think it's 155. Dude, I know shit. So the average here, and this is a population. This is everybody, correct? This is the whole company. So the average is 155,000. That is the average salary at the company, correct? What is wrong with me being told, oh yeah, you could expect around 155,000, that's the average? Is that an accurate thing to tell somebody? No.
No, because it's not, right, like there's different levels. Like in San Diego, like you give someone an average, but a house in La Jolla costs a lot
so
different than a
houses,
house
now
in,
you
like,
see the thing about the
Humboldt.
houses. I like to walk around La Jolla and just look at the houses that I'll never be invited into even, not let alone own, right? I'm like, oh, okay, oh, look at that, I'm sorry, okay. So what's a better thing to tell somebody? We've actually talked about this. I don't think I called it this word. But what would be more represented? What wouldn't matter? What if the CEO gave himself a raise, 800,000, right? The mean would definitely go up even more, correct? But there is a certain number I could calculate that wouldn't care about that.
I don't know what you were after 155 plus.
Oh, 1,000. Sorry. Yeah.
Sorry.
Yeah, because these were in the thousands. Thankfully, they weren't making $38 a year. You know, that wouldn't go very far. Okay. So my point is this: there is a certain word I can call P50. What was P50? Where's P50? That's the number that's right in the middle, basically, right? So 50th percentile. So it's always going to be right in the middle. What is P50 here? 41. Right? $41,000. Isn't that a more appropriate thing to tell somebody? The official name of this, besides Q2, is another name. The official name for the number that's right in the middle. What goes right in the middle of a road? The median. So this is what's called the median. And the symbol for median, it looks like a mean that had a rough night or a really good night. Just his little hat got all crumpled. Poor little dude. Somebody sat on his hat. Isn't that a more appropriate number to, in fact, what are these both trying to do? They're both trying to find the middle of the data somehow. The average is a sort of middle. The median is a sort of middle. Sometimes the average is the better one, sometimes the median. When is the median? What was it about this data that made the average suck? There is an outlier. Cool. So whenever I have outliers in the data, the median is a more accurate representation of the center. You guys with me? But the mean is more generally useful, so it sort of wins. We're going to use the mean a lot more than we're going to use the median. Okay. Why does it win? Because it takes into account all the values. Does the median change, like I said, if I make that 900,000, does the median change? Because the median is just whatever's right here. So if I change this to be 1,500,000, right? 1,500,000, does the median change? Nope. Still right in the middle is 41. Okay, maybe. Okay. So at home prices, you'll see, I pulled up a website, I'm not going to show it to you. If you just search home prices, they'll always say median price, always, because that's the only one that makes sense. Okay. So we have the mean, we have the median as a way to determine what the center of the data is. Both of these, what kind of data do those work for? Let me try to say this again. What's the two main types of data? Qualitative, quantitative. These only work for what kind? When am I able to add up? Can I add up hair colors? No. So what kind of data do these work for? Quantitative. I love it. So do I always have quantitative data? No. Don't I sometimes want to know where things seem to be clustering in qualitative data? Yes. So we have another idea called the mode. This poor little dude doesn't get a symbol. One semester a student felt bad and said, can we make a symbol for it? I'm like, sure, and we made capital M for the mode, but it doesn't happen. So the mode, you hear the word mode like pie a la mode? So if you want to get, do you know what pie a la mode is? Yes? Pie with ice cream or whipped cream? So don't you want more and more? And me, I get like a little piece of pumpkin pie with like a ton of freaking whipped cream. Right. That was me, sorry. So mode is the thing that occurs the most. So it will obviously work for qualitative data. If I go out and see the types of cars in the parking lot, I can tell which type occurred the most, correct? And that would be useful information to have. You with me? Okay. So it works for qualitative data, like I saw 40 BMWs, and I always go for BMWs and freaking Hyundai, whatever, that doesn't matter. I can figure out which one occurred the most. Blah, 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 blah. We're obviously going to use more for, it still works for quantitative data too, so obviously, if this is my data, what's the mode? Holy shit. So the mode is 2. What's the mode for this set of data? Yeah, it's bimodal. 2 and 4. Now we only go up to trimodal. If there's more than that, we just go, okay, holy shit, there's no kind of place it's clustering. Does that make sense? The mode kind of gets a feel for where it seems to be clustering. And if there's more than 3 of those, it really isn't clustering anywhere. Okay, maybe? So the most you'll see is trimodal. What about this data? What's the mode? 5. There's a clear winner. So it isn't just all the ones that have more than one, it's who wins. 5 won. So the mode is 5. Okay, that's pretty nice, right? You gotta love that shit. Average, you guys come in knowing. You got the formula now. Greek letters, but we're okay. Mode makes pretty much good sense. Mode most. Median, middle of the road, beautiful. Some of you guys came in knowing that, not everybody did. There is another one. There is another. I'll tell you that real quick. The book doesn't use this one, and I probably won't ask you, but I just want to tell you. There's something called the midrange. What was the range again? High minus low, right? So doesn't it make sense the mid-range is the number in the middle? of the range, the high and low. So the mid-range would be the average of the high and the low. So that's another way to kind of tell where the middle is. Okay, maybe. Okay. Yeah, cool. So these are all ways to try to tell where the middle of the data is. That's what these all are. So with that in mind, I've got a very simple little thing. How many people are here today? Let's see. 5, 10, 15, 19, 23, 33, 43, 45. Interesting. Okay, I can almost do this, damn it. All right, so let me give this to you, and then I'm going to try to put you in groups of 4, and you'll see why in a minute. And you're going to need a calculator. So if you need a calculator, get your ID or whatever out, but give me a moment to get back to the front. There's something behind you?
Yes.
Oh, that's right. So it's even a little worse. Got exactly enough. Kind of sucks because now I don't have one for me, but too bad for me. So what I want to have happen, to see if you guys understand why, I want you to group up into groups of 4. Because how many data sets are on that sheet? 4. So if you have groups of 4, one person can calculate A, one person can calculate B. Do you guys see what I'm saying? So instead of me counting you guys off and making you all get up and move around, can you guys just find 4 people near you? There's going to be 2 extra, just the way it is. So you're going to have to, if you need a borrowed calculator, come on up, and then group up with other people. Check before you walk too far away to make sure the battery's good. It should all be good. Dadgummit. Let's see if we get a second one. Oh boy. So, all the answers to the first question are 13. I have 2 colors. Okay. And then part 2, I've given all my handouts away. So part 2 says, are all the data sets the same? They're obviously not, correct? Yeah. Does that agree with the fact that in part A you found they all have the same measure set? No. So for example, guys, I'm pretty sure you all know there's a website called Rate My Professor, for example.
Yes.
And where you can go and get this, and I always like to tell my students, if I don't get any bad reviews, then I'm not doing a good job. There's certain students I want to get bad reviews from. I don't know if you understand what I just said. All right. Did you know that beyond that, there's a website that will actually give you the grade distributions for teachers? Did anybody know that? Because that's public domain knowledge. You could actually call this college and say, I want the grade distribution for Mr. Waller for the last 10 years. And it's public domain knowledge, right? So go for it. So all that is to say this. Let's say you're trying to figure out which class to take for next semester. And these 2 teachers have like the same Rate My Professor, the times work fine, both of them. Everything's the same. They even give the exact same average grade. They both give an average grade of C. You with me? But you do know that the one teacher gives everything, and let's say we're at university. What I mean by that is, what's failing here? D, right? D doesn't transfer. D is basically failing. You guys with me? At university, do you all understand that D is passing? Did you all know that? Yes? No? Okay, this is scaring me because some of you guys are like not reacting at all when I ask a question, and that's freaking me out. I'm like, I don't want to play poker with most of you guys. You know, like keep asking. So some of you, at university, you can make a D and you can pass. That's a passing grade. So let's say you're at university. These two professors are the same in every respect. They're almost like clones of each other, except this one professor gives A through F with an average of C, and the other professor gives B through D. You with me? You, everybody. Which professor would you take? To me, it kind of depends, right? So, if I knew I was going to kick that class's ass, it's a difficult thing to say, I would not want to take the person that never gives an A. You with me? It happened to me. I kicked this class's ass, and the guy was like waiting for some deity to take his class and finally give him an A minus. Got me a B, and I'm like, ugh. Anyway, sorry. So if I knew I was going to really do well in the class, I'm not going to take the guy who never gives A's. You with me? But what if I thought, I'm going to suck in this class? I might consider taking the professor that seems to never fail somebody, right? And again, as a teacher, not the greatest thing, all right? But still, I understand. As a student, I would have definitely thought about that. Are you guys all with me? So what is the extra information? They both had the same average, C. In fact, we'll even go further. They both had an average of 73.893, right? What we knew, what the extra piece of information we needed was how widespread, how spread out were the grades. If I know those two things, I don't care, I could have 1 billion data points. If I know where the middle is and then know how spread out from the middle it gets, I have a pretty good feel for that data, just from those two numbers. So looking at this, what did you guys get for group A, data set A? What did you get for this frequency distribution?
1, 0.
Oh man, you're even dying. I think it's the heat. All right, I'll just use this. Poor little dude. So 10801. So if I consider the mean to be like home, this one did not get away from home much, right? You're with me, okay. All right. What about data set B?
1, 2, 4, 2, 1.
Okay, I love it. And then this guy was the we call this a uniform distribution because when I think of uniform, I think same. Everybody's got the same thing they're wearing. So there's a uniform distribution of every class gets the same amount. And then D was, I think it's 3, 1, 3, 1, 2, 1, 3. Okay. So who is the least spread out? And I'm going to kind of force us to realize that spread means who gets away from home, who gets away from the mean the least. Obviously, A. Who gets away from home on average the most? I hear a few C's, but there's a clear winner here. If this is home, do you see how more got up further away? Didn't 3 get like really far away? Or, you know, relatively far away? So this idea is the idea of spread. So we're going to actually construct a number. This number is going to represent how spread out my data is. So just to give you guys an example, when students take a quiz, the normal number for the spread of the quiz grades is around 15. So the average distance that students' quiz grades got from the average is about 15 away. You guys kind of with me? So when that becomes 25 or something, that means that somebody got a really low grade and somebody else got a really high grade. You see how that would cause the spread to become bigger, right? And if my spread was like 5, that would tell me I constructed a really bad quiz because everybody scored almost the exact same score, which is normally my fault for making a bad quiz. Okay. So this whole thing was just to show you, if I know the mean of a set of data, that's not enough to differentiate it. But if I know the mean and the spread, those two together tell me a lot about the data. I don't have to see all the frickin' data points. Just give me those two numbers. So this entire semester, we are going to learn different ways to get data. One way is just for me to give you a list of freaking data, right? We're going to learn all these different ways. Every time we learn a new way to be given data, we're going to learn a way to figure out the mean and the spread. And I might as well call the spread the actual name. The name of the spread is standard deviation. I knew some of you guys knew that. All right. So, are you going? I don't know if I turned the guy on. Yes. How you guys doing? Does that kind of make sense? Yeah. Okay. It's just it's kind of like the 5 number. Give me a moment. It's kind of like the 5 number summary, yes. So that's got 5 numbers and it summarizes the data. So if I had 1,200 data points, I can give somebody the 5 number summary and that gives them an idea. This is even better. I can just give them where the center is and how spread away from the center it gets. And that gives me an idea about the data. I like it. So, did everybody finish that up? You guys all with me? Okay. We got a little bit more to do. So what we just did, just to make sure you guys are all with me in the book, because this is my worst thing. I'm never really good about this. 2.5 is the measures of center. So that's the mean, median, and mode. And then the mid-range I kind of gave you. They don't really tell you about the mid-range in the book, I don't think. So 2.5 is not, in fact, for the homework for 2.5, you might realize I only assigned 3 problems because there's not a lot in 2.5. Just mean, median, mode. The thing we just talked about, the idea of spread, which is really standard deviation. And we have not covered this at all. I've just told you what it is, what it means. We haven't talked about how to calculate it yet. That's actually in 2.7. So let's go back and talk about 2.6 real quick. (2.6) talks about the possible shape of distributions. So can somebody tell me a word that would describe this shape? Say again?
A bell curve.
Bell curve. Anybody else know a different word? Normal. It's normal curve. Can somebody tell me not the name of it, but one aspect about it? How did you know that it was a bell curve?
Symmetric.
Symmetric, kick-ass. So this would be a very specific example of a symmetric distribution. Just to make really sure you guys understand why that is. If I drew a line down the middle, isn't that like a mirror? Okay. Could you draw something that is not a normal curve, but is still symmetric? Go ahead, try. And then I'll draw one and we'll see if it's the same. No, just draw a picture that's not a normal curve, but it is symmetric. Does everybody understand what I'm asking? Go for it, try. Some of you guys are like, no dude, I'll just wait. No idea what you're talking about. So it just has to be a reflection of itself. That's all symmetric means. So this is not the only way to have a shape that's symmetric to itself. Any damn thing, but it's got to be, something up here, right? So this wouldn't work. That's not symmetric, right? That's not good. Let me ask you this. How many modes are there here? It's unimodal, right? One mode. So the most common thing I see if I ask for like another symmetric distribution would be something that's bimodal. Did anybody, what kind of shape did you draw? Can you do it in the air? Anybody want to show me? Aw. Okay, I like it. So I wasn't really specific. So yeah, you could have a shape. A heart is symmetric. Aw. I sort of wanted one that was kind of like, had an x-axis to it, right? So that one kind of matches with yours, which is kind of like an M, right? How many modes does it have? Bimodal. Is that symmetric? If I draw a line down the middle, if I pretend like that's the middle, doesn't it fold on itself? Okay. Good? Okay. All right, nothing amazing, yes?
I basically just did that. Like I did like that. Does that still kind of symmetric?
Do it again, do it again.
I did like that.
Okay, cool. Yeah, so you can do like this.
Yeah.
Kick ass, even make it like that even, right? I love it. Kick ass. So it
That's
just has to
symmetric,
be, the middle line is the folding point where it would fold on itself. That's all you need for symmetry, right? So a normal curve is one example of a symmetric distribution. Kick ass. Now, think of this as, do you guys all know what taffy is? All right. If you don't know what taffy is, it's this really chewy thing. You can bite into it and you pull it. It's like stretches. Have you ever seen Stretch Armstrong? Before we had Nintendos, we had Stretch Armstrong. You stretch this guy and then you go back to normal and you just sit in the corner going, create video games. So if I think of this as a mound of taffy, if I grab this side and I pull it, can you guys all see what would happen? It would kind of do like this, right? You guys with me? Okay. Which way did I pull it? To the right. So this is called skewed right. Later this semester, we're going to see a distribution that is skewed right that we're going to use a lot. It's going to be like this general distribution we're going to use. I sometimes call it the Jabba the Hutt distribution because it looks like he's got a big tail. Oh. Now, incredibly enough, if I would have picked this side and pulled, what do you think that would be called? Holy crap, okay. So whichever way the tail kind of goes, whichever way it extends further than it should if it was going to be symmetric, that's the way it's skewed, right? Okay. How we doing? Okay, some of you guys always look like you're pained. I'm sorry, you're in pain. Okay. 2-6, that's really, 2-6 gets a little bit deeper into stuff. Let's do a specific computational example. We make up some data real quick. What if I had 1, 2, 2, 3, 3, 3, 3, 4, 4, 5, 8, 9, 15. Bless you. Real quick. So that data. So write that down real quick. I could make a histogram out of this. Let me see if we need to. Can you guys tell me, now real quick, is that symmetric data? Do you have to draw a picture or can you understand it's 1, 2, 2, 3, 3, 3, 4, 4, 5, 8, 9, 15. So it's not symmetric. Does anybody see which way it's skewed? I love you guys so much. So it would be, maybe we'd have to graph it. So it'll be 1, 2, 2, 3, 3, 3, 3, 4, 4, 5, 8, 9, 15. So let me ask you again. Which way did I pull it? Ah, so it's skewed right. Yes? Because it goes, I'm normal. Oh, shit. It's got a big tail that way, correct? Okay, so a bulk of it is here, and then there's dribbles over that way. Okay. Take a second and calculate the average. Oh boy, what is it moving? 4 point something.
4.769.
Yeah, okay. So the mean is about 4.769. What's the median? Yeah, the median is 3. So this is a very concrete example of a generalization we can make. If it's skewed right, isn't the mean going to be, in fact, this should even be further because it's 15 by, oh, you get it. Won't the mean be affected by those larger numbers that are there? If it's skewed right, the mean will always be bigger than the median, because it'll have a few extra numbers that are larger than the rest of it, so the mean is going to go up where the median isn't going to know about that. It's just going to stay in the middle. If it's skewed left, then the mean will be less than the median. So you will see some questions in 2.6 that relates to this. You can always read the section too. It's crazy. Okay, I like it. You guys all semi with me? Okay. Oh, this is awesome. All right. So we're going to do we're going to develop the formula for figuring out the number that represents the spread. I'm going to do that right now. So this is something you guys didn't get to see much in like algebra. In algebra, did we just basically mostly give you formulas? You didn't get to see a lot of what went into creating them. And some of you guys are like, I am so fine with that, Jeff, but too bad. I'm going to show you where this equation comes from. So I want to make 2 sets of data. Let's say, what you got, Jeff? Sure, I like it. Okay, that's nice. I like that. So there's one set of data. Here's another set of data. What's the mean for both of these sets of data? What's the average for both of those? So they both add up to be 20, and there's 5 data points, so 20 divided by 5, 4. So the mean for both of these is 4. What's the range? Both of them is a range of 6, right? Okay, so the range is not good enough to tell me, to kind of like capture the difference. They're obviously not the same set of numbers. So this is a lot like the one we just did. But now we're going to get really specific about this spread number I was talking about. Which one should have a larger spread, remembering that spread means the average distance the data points get away from the middle? Which one gets further away from its middle on average? Set 2, yes?
Yeah.
Set 1 has 3 data points that don't get any distance away from its middle. But set 2, everybody except this dude left home, right? Here the parents are like, oh God, get out of here. Okay. Oh, so you guys are like, yeah, it's basically okay. So, okay. All right. So we're going to figure out how to construct a formula that will do what I want it to do. This is something you guys don't get to see very often, but it's so freaking cool. This is the power of math. I want a number that means this. Okay, well, let me make the math do that for me. Let me make it tell me this. So let's do this. I'm going to do set 1. So let's write it like this. This is a little more useful to write things like this. Let's do set 1. So let me ask you a very silly question. If I wanted to calculate the average length of everybody's left shoe that you're wearing, what would I need to do first? I need to get a bunch of lengths of your shoes, yes? I can't average something until I have a bunch of those, yes? Go with me now. I'm going somewhere. The spread number, the standard deviation, is supposed to be the average distance that every data point gets from the mean. So if I want the average shoe length, I need a bunch of shoe lengths. If I want the average age, I need a bunch of ages. I want the average distance from the mean. So what do I need to construct first? A bunch of that represent no distance from the means. I'm going to pretend like this. Okay. So again, so if I want the average salary, I need a bunch of salaries. If I want the average age, I need a bunch of ages. I want the average distance from the mean, I need a bunch of distance from the means, right? Or distances from the mean. So I want to do this, basically. And actually, let's do this, sorry. This is, I'm calling this a population. Populations, we often think of populations as being very big. They could be any damn size, right? So I can have a population of 5, and I do. There it is. Okay. So, for example, and the mean here, of course, was 4, right? So this is really x minus 4. So here, for example, this would be -3. Is that cool? So you can think of that as meaning it was 3 below. This is 0. Good. 4 minus 4. 0. 0. 7 minus 4. 3. Kick ass. Probably won't go any lower. Oh. Okay. Now, real quick, if I add those up, what do I get?
0.
If I do this for any freaking data, any freaking data, if I do every data point minus the mean and add them up, I will always get 0. There will be equal amounts negative as there are positive. Does that make sense? So this, you're like, thanks, Jeff. That's useful. We always get 0. So the main problem is I have some negative numbers. You guys with me? What's one thing that mathematically we could do that would kill the negative? What is something very direct that would take the negative away? I think I heard it. Add what? Add a positive? No? What function makes everything positive that I put into it? You guys know this. It's like, I heard it. Not square, not yet. Square is going to be the right answer, but right now, absolute value, yes? What's the absolute value? I know I heard it. I know somebody said it. What's the absolute value of -7?
7.
Why? What's absolute value based on? Do you guys know? Distance. So how far away from 0 is -7? 7 away. You would never say that you're -4 feet away from me, even if I turn around. You're still 4 feet away from me. -4 would mean like, Quaid, you're in me, son. Right? That's weird. Stay out. Okay. So I could take an absolute value here, and that would make everything positive, and then it won't add up to be 0. The problem with it, do you guys know what the absolute value function looks like if I graph it? Does anybody know? Remember how a parabola looks like a U? I mean, x squared looks like a U when you graph it. Does anyone know what a, yeah, maybe, sort of, almost, kind of? Looks like a V. Right, so you don't have to draw this, but an absolute value, if I draw it, it'll look like that. Is that a plane you want to be on? You drive, hey, we just hit 30,000, everything's fine, and BAM! You turn 90, you just turned, you're all dead, right? You don't want to be on that plane. You guys with me? There's actually, what I just said, doesn't sound like math, but do you all agree something very strange is happening there? Do you all see, what's the slope here? Isn't the slope negative? And then doesn't it instantly become positive? Okay, that's harsh. This is what we call, it's actually called a kink in math, believe it or not. So there's a lot of problems with that. So instead, I'd rather do what you guys said. Another way to kill the negative is to square. And what's the square look like I just said? The next square looks like this. That's a plane ride we could survive, right? And we're turning, oh, and then we're okay. We're not slammed up against one side of the plane. Okay, maybe. So just to let you know, there are two ways to kill the negative. We're going to choose to square things. Now, what does that mean at the end? If I'm squaring things right now, at the end I'm going to have to square root. Because if this means the number of dogs people own, then this is going to be square dogs. Okay, that's strange. Again, I don't want to come to your house if you have 0.7 dogs or if you have 3 square dogs. I don't know what that means. Okay, so I'm going to do this. Why am I squaring it? To kill the negatives. Otherwise, it'll always add to be 0. So then I get 9, 0, 0, 0, 9. Now, I want to remind you guys, the standard deviation is the average distance every data point gets from the middle. So everything we're doing is trying to get to a point where I can find the average. So how do I find the average? Add them all up, divide by how many there are. Yes, that's the average. So I need a list of distances. Negatives suck. Okay, I square them. Now I'm going to add these up, divide by how many there are, and then at the very end I'm going to have to take a square root to get everything back to normal dogs instead of square dogs. Okay. Okay, maybe. So if I add these up, so let me write this very technically. If I add these up, if I sum up these, what do I get? Some of you guys can't even see that, can you? I'm sorry. 18, it's crazy. So the spread, which is the standard deviation, for a population, it uses the symbol lowercase sigma, which kind of makes sense because it's standard deviation spread is going to use S, because math people are very creative. So uppercase sigma looks like an E, lowercase sigma looks like a fat R. Oh well. Okay. You guys all with me? So that's that symbol there. How do you make it? Start at the belly and then go out to the cap, right? Start at the belly, go out to the cap. I always get people who just write R. R means something else. So I want to keep you away from just making it R. So when I calculate this, I'm gonna calculate first sigma squared because, like you said, at the end I got a square root. So I haven't square rooted yet. So let me see. Let me balance the room out a little bit. I'm going to do this over here. There. So this is going to be, I add up the squared distances and divide by how many there are. That is an average, correct? That's an average squared distance. So of course, again, I'm going to square root at the end. So what is this whole damn thing? What do I put there? What is the sum of all the x minus mu squares? 18. I really want everybody to understand. Algebra, you are so used to putting a number into a single letter. This means the sum of all these things. So this whole damn thing gets replaced with what the sum is, 18. And then what's n? 5. So sigma squared is 3.6. Kick ass. This has a name. This poor little dude, because we're going to square root him, but he's got a little name. He's called the variance. And we'll talk more about him later this semester, but for us right now, it's just like we're just not done yet. We still have to square root to figure out the standard deviation. So if I take the square root, what do you get? Sounds about right. 1.897?
Yeah.
Were there other numbers after it?
Yeah.
Okay, so the next one's a 3?
3, 6.
Okay, gotcha. So here's the thing. You ready? Here's a huge thing. Whenever we have standard deviations, we need to round them to at least 3 decimal places. So you can go more if you want to. Don't go 11. Holy shit. Right? Go at least 3 decimal places. Are you guys all with me? 11. Okay? So this represents the average distance that every data point got from the middle. Okay. So I want you to try to do everything we just did, but for this data. Do everything we just did, but for this data. Can somebody predict for me, will it be bigger or smaller than this? What did we say? Which one was more spread out? Which one got away from home more? Set 2. So the thing that measures how spread out it is should be bigger for set 2. So go ahead, try it. I'll give you a little light at the end of the tunnel. As soon as we're done with this, we'll call it a day. Go for it. Still 4. Let me just put mu there because that's generally true. I'm going to sort of catch up a little bit to you guys. Make sure everybody's doing the right thing. There's just a couple things that change because this is almost the same data, right? So still 1 minus 4 is still negative 3. 2 minus 4 is negative 2. That still adds up to 0. So we always have to square to kill the negatives. Is that all right? I'm going to show you a couple things in the calculator after we do this, but I'm making you do it fully by hand at least one time. Now I just take, what is the sum of those? 26. So then that's what I put up here. 26 divided by 5 is 5.2. And what's the square root of 5.2? 2.280. Okay. which is obviously bigger than the one we got before, which jives with what it should be. It's more spread out. The freaking number that measures spread should be bigger.
And this is 2.6.
This is 2.7. Real quick, don't do a damn thing and tell me what the standard deviation of this data is. What's the standard deviation? You can do it. Standard deviation is the average distance from the mean that the data points get. 0. I love it. So the smallest that a standard deviation could be is 0. It can't be negative because that would be weird as shit. What does that mean? Again, you can't have negative distance, so standard deviation can't be negative, right? So let me show you a couple things in the calculator, and then, like I said, we'll call it a day. You guys all look a little fried. I know I contributed to that. Let me see if I can just not put students on here. Okay. Scheisse. Whoa. Okay. Okay. So this is like one of the main spots we're going to go to. We're about to analyze data. We've got to tell the calculator what the hell the data is. So let's put in the data we just did. 1, 2, 4, 6, 7. And we actually did what we're about to do. We did it once already, but I just sort of like went straight to the bottom of the list of stuff. How many variables again are there? Nope, there's 5 values. 1 variable. I love it. So we're going to go to stat, calc, one bar, right? And you guys, some of you guys might say 1 bar stats on the screen. Just hit enter because it defaults to list 1. Or you might have this. You got to hit list 1, no frequency list, calculate. Okay. Does anything up there look familiar? Yes. This is what we're going to talk about next. I'm about to say a phrase. We're not done yet. The S is what we're going to talk about next time. Today we're talking about the sigma. Sigma is population standard deviation. S is sample standard deviation. So let's do this. Come back here. Go to list 2. See how I have list 2 highlighted? I can control the whole damn list. So looking up here, list 1 is my X's. Check. List 2, what do I want list 2 to be? I want list 2 to be my X's. Where are my X's? List 1. So I want list 2 to be list 1 minus the mean, right? So watch. If you go up to list 2, and you see at the bottom it says list 2 equals what? Second one, L1 minus 4. Okay, sweet. Because on a test, on a quiz or a test, I'm going to want to see this on your paper, right? After test 1, I'm never going to make you do this again for standard deviations. We're just going to take it right out of 1 bar stats. You guys with me? But until test 1, in your homework, you got to do this. On a quiz or a test, you got to do this. So what's L3 going to be? What do you think I want L3 to be? We just did what here? We just took
L and L2, and then we put it in where X is.
Careful. So what do I want to square for L3?
L cancel.
L2, yeah. That might be what you said. I'm sorry.
Yeah.
So L2, if I go to L3 and I say make that L2 squared, I get those, right? 94049. Now, real quick, this is a very small set of data, but you know I'm going to give you like maybe 16 data points, and you might not want to do all this by hand. You could just have the calculator do it and copy it. How do you make it add list 3 real quick? Well, here's the way to do it directly. Hit second mode to quit. What's right above the stat button? List. So that's where I could do stuff directly to my list. Because right now I want to sum up a list, correct? I want to add list 3. So go to list, hit second stat. I want to do math to a list. I want to sum up a list. I want to sum up list 3. And there's the 26 that we got, right? And again, very small set of data. I didn't need to do all that shit. But if I have like 20 data points, I might rather have the calculator do most of the adding and stuff. Are you guys understanding that? Okay. I think, why don't we have a nice early day today? How's that sound? So next time we'll do sample standard deviation. I'll have a worksheet about standard deviations, and I'll have the quizzes graded. If you need to see me come up, don't forget your stuff.